plus direct plus the units. This is how you have to answer. And if it is just a scalar, then this direction won't be present. That's it. Okay. One thing, this first question was completely right. Question from your NCRT. Question 2, you have done this fine. The resistance was given, magnetic field given, area given, number of turns and everything. This you haven't done. What is the maximum current drawn from the generator? That you wrote it very, very well. It says number of turns are there, area is given, N is given, A is given, B is given, and the resistance is given. Yes. So, is there anything? Yes, omega. Omega is also given. So for current, you said the EMF is equal to NBA omega, maximum EMF. So maximum current will be maximum EMF divided by resistance. So that will be NB omega by R. Yes. Now it says, what is the flux? This was missing in your answer sheet. This part was correct. What is the flux through the coil when the current is zero? What's the value of flux when the current is zero? And what is the flux when the current is maximum? This basically says that when the flux is zero, when the current is zero means this whole term is zero.
Yes, ma'am.
EMF will be zero. Now, E is equal to minus d phi over dt. Is it?
Yeah. Yes, ma'am.
So if this is zero, what is the flux? There is no change in flux. Flux won't change. You calculate it using NBA. That's it. There is no change in the flux. Got it? Because EMF is zero, no change in flux. So there won't be any change in the flux. So when it says what's the maximum flux, and second part says no, when the current is maximum. Current is maximum is the case that you've calculated in the first part. Yes?
Yes, ma'am.
So this is basically here time. Did they mention the time? Number of turns, area, magnetic field, resistance, omega. No, time isn't mentioned. So it says what is the flux when the current is maximum? See, when the current is maximum, that means your EMF is what? NBA omega. Yes?
Yes, ma'am.
Isn't it? Isn't it? NBA
Yes,
omega.
ma'am.
Now see, NBA omega, our equation now this time won't be zero. Whatever you get, NBA omega minus d phi over dt will give you the value of the flux from here. Yes. So see, EMF will be calculated from this. And it says what is the flux when the current is maximum? Maximum current is achieved. What is the flux? Because we have studied, what have we studied? We have studied that the values of this is all about the AC generator, right? So see, in AC generator, when you're talking about the EMF depends upon the rotation of the coil. Okay, if the coil is rotating maximum to its maximum, then we say sine 90 degree has been formed. Here rest of the sine theta, sine phi is also present. So this is the flux current maximum or current zero is determined by this equation only, that when the current is zero, see, we have seen that flux and magnetic field, they influence the current. So when this current is zero, what is the value of this flux? And when the current is maximum, what is the value of this flux? Okay, this is what is meant by the question. And it says, would the generator work if the coil was stationary? And instead the poles pieces rotated together with the same speed as above. So this won't happen. See, if the coil was stationary, then there won't be any omega. Omega will be zero. Rotation of the coil is zero. Omega is the rotation of the coil. It's not the rotation of the magnets. It's the rotation of the coil. If this is zero, you won't have any EMF. Induced EMF won't be there. No induced EMF, no induced current. How will we have the AC generator working? Got it? And one more thing I found here, your answers were right, but why haven't you written any explanation for the answers that I mentioned? I think I didn't give all of them. I gave few of them, especially these ones. So we have studied, I think when we did in the class, after every coil we did an explanation that okay, this is from north
Yes,
to
ma'am.
south. So what's the aim? The north approaching north pole is the problem. So it will try to move it back. We did these questions. Same questions they aren't
Yes.
they? So
Yes,
see,
ma'am.
this assignment, please do it again. This assignment,
Okay, ma'am.
at least just do it and share the PDF on WhatsApp with an explanation because this is a very important
Okay,
topic
ma'am.
and you take out most of the questions. Most of the questions have Lane's law. And see, right now options were given, but these options aren't actually there in the exam. This is a previous year question where it was just a question
Uh,
with a question mark. No options were there. So you have to write it from your side. Got it? I
okay, ma'am.
want once. Okay. Just share it on the
Okay,
WhatsApp.
ma'am.
Okay. I hope my voice is audible. You're able to see the screen. You said you have a bad network
Yes,
today.
ma'am.
It is fine.
Yes, ma'am.
Okay. So we were doing LCR circuit, series LCR circuit. We saw the phasor diagram. Phasor diagram is the most important one from the series LCR. Okay. It has been recently said in the CBSE board exams that phasors are the most important from your series LCR. In fact, some of the syllabus, not the syllabus, but some of the books have this that only phasors are going to come from series LCR. So phasors are very important. Just pay attention to the phasors. But anyways, we'll have to do
Okay,
everything.
ma'am.
So we did this equation z is equal to under root xl minus xc whole square plus r square as the impedance or xc minus xl, that depends on whichever value is greater. Until here we've stopped. Could you go through the assignment?
Yes, ma'am. I went through the assignment. I haven't
Okay.
submitted it.
Okay. And did you go through the notes?
Yes, ma'am.
At least till here, have you gone properly?
Yes, ma'am.
Okay. So see, let's practice a question. Now pay attention to the chapter EMI. Start revising it properly. Okay. Once EMI, because
Okay,
in the
ma'am.
next test, I'll give the complete chapter EMI. So start studying
Okay,
it.
ma'am.
This week you won't have, the next week you will have the EMIs test. So
Okay,
determine
ma'am.
the impedance of a series LCR circuit, the reactance of capacitance and the inductance. What is this given?
Uh, The XC.
Yes, reactance of capacitance means XC. That is the capacitive reactance. It is given as
Yes, ma'am.
250 ohm and inductive reactance
And
means
XL.
XL. Very good. That is 220 ohm. So which case is this?
C and XL.
What?
Both are given. So is it the impedance triangle? Do you follow that?
No, no. Which case is this? For impedance calculation, I told you case 1, case 2.
Yes, ma'am. Uh, C is greater, so it's case 2.
Yes. Don't
XC
remember
minus
it like
XL.
case 1, case 2. Just tell me XC is greater in this case. So we'll use XC minus
Okay.
XL equation. Yes. Because how will you
Yes,
remember
ma'am.
that 1 and 2? Okay.
Hmm.
So just remember it like this. XC is greater than XL. Okay. So this is this case.
Yes, ma'am.
XC is greater. Resistance is given as 40. 40. Impedance is equation Z we are going to use as XC minus XL whole square plus R.
Plus R square.
Yes. See, from the cases that we did, one case was this, one case was this. Whenever you are
Yes.
specifying these equations, don't write these cases, just write it like this. XL, since XL is
Okay,
greater than
ma'am.
XC, XC is greater than XL, this is the equation. Okay. So let's put
Okay,
it
ma'am.
Z is equal to 250 minus 220 whole square plus R square, resistance is 40 square. Then we have under root. Z, this is 30 square plus 40 square under root. So this is 1600 plus 900, 2500. So 50. 50 ohm is there. What is 50 ohm? 50 ohm is the impedance, means it is the total value, the complete total value of the resistance of this circuit, which has a resistor also, inductor also, capacitor also. Yes?
Yes, ma'am.
Okay, so write down this question, then one more concept we'll discuss.
Okay, ma'am. I'm done, ma'am.
See, Basmi, in this question, It is what will be the readings in the voltmeter and ammeter shown. So before you solve anything in this question, if you notice one thing here, the values of XL and XC are equal. Can you see? Both are equal to 4 ohm. Yes. So
Yes,
this
ma'am.
condition is known as the resonance condition. The resonance condition of the series LCR. That is our next topic, and it's a very, very important topic from your LCR circuit. Okay, resonance often comes in the exam to write about the conditions of it, to solve the numericals also. So resonance condition of series LCR circuit, XL is equal to XC. Now, when XL is equal to XCC, if I have XL and equal to XC, so look, in the next step, I'll cancel them, both are equal. I'll be getting Z is equal to under root R square, which will be Z is equal to R. Now see, from here, we were getting such a big denominator earlier. Now we are getting a less denominator. Current is inversely proportional to the impedance. If impedance is decreasing, impedance is now only equal to R. Like look at the previous question which we did. It's like if impedance was 50 ohm, now it is coming only 40 ohm. Because even after solving everything, putting the under root, subtracting and all, you are getting a bigger number. But now only equal to one of its component, that is resistance. So it will definitely decrease. So when Z decreases, what happens to current? It increases to its maximum value. Yes. So this is what is the condition of resonance. How we have to define resonance in the exam. One thing you are going to say that XL is equal to XC. This condition you'll have to mention. Okay. That the inductive reactance is equal to the capacitive reactance. This you will be mentioning. Second thing you will mention that this is the condition where the current is thought, or here the current becomes maximum because the impedance becomes equal to R. So this current is maximum condition has to be specified. Two conditions you have to specify these two. Actually this is just one single condition only, that XL is equal to XC. So these are the things that are happening. Remember, here you'll have to mention that current will be the maximum because XL is equal to XC. So these two things, many students just write XL is equal to XC. That will not help. Okay, when resonance come, you write it till as it is. Just explain this. So XL is equal to XC. A series LCR circuit is said to be in resonance when current through it has the maximum value. This is what I was saying. Current will be maximum here. So Z is equal to R. Impedance will be minimum, but current will be maximum. Okay.
Okay, ma'am.
Now, if impedance is minimum, value of Z is just equal to R. Yes, we can say XL, if XL is equal to XC, we can say Z is equal to R. Yes, this is the value what we can say. If Z is just equal to R, then our current IRMS will be ERMS by Z with you using, but your Z is equal to R, so you can use this. If I talk about I naught will be equal to E naught divided by Z, and Z is equal to R. So same equation, same thing, you just put the resistance as, you put the impedance as R. Okay. Talking about the frequency, see, XL is equal to XC. What's the formula of XL?
XL was L and one
XL is
more.
equal to L?
No, ma'am. There was 1 by L. No.
Look into the notes. If you're forgetting, check your
2
notes.
pi frequency. 2 pi frequency.
2 pi frequency into L. In terms of angular frequency, it is?
In terms of angular frequency, it's WL. XL is equal
Omega
to
L.
WL.
Yes. And
Yeah,
XC?
omega L.
Check XC.
XC is 1 by omega C.
Yes. Remember this formula. Without these, you will not be able to solve the questions. Now see, if I shift this and bring it here, means omega into omega, 1 by LC. So omega square is equal to 1 by LC. So I can say my angular frequency is 1 by under root LC. So what is omega? Omega is the angular frequency. Okay. Now, what's the relationship between angular frequency and linear frequency?
2 pi nu.
Omega is equal to 2 pi into nu. So the linear frequency is equal to omega divided by 2 pi. So 1 by 2 pi multiplied to omega. What is omega? 1 by under root
1
L.
by root L.
So omega divided by 2 pi. And what is this? This is the linear frequency. So this is often asked in the exam to derive this linear frequency one. Okay, so when you have to derive it from here, starting from these steps, derive them. Okay.
Okay, ma'am.
All right, we'll practice a question. First, you write it till here.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, done.
Okay, see, this question says a resistor of 12 ohm, a capacitor of reactance 14 ohm, and a pure inductor 0.1 Henry are joined in series and placed across a 200 volt 50 hertz AC supply. You have to calculate the current in the circuit, phase angle between the current and the voltage, and it says take pi as 3, not 3.1. So see, what is this? Just tell me the symbols for each of them.
12 ohm.
What?
It's no, ma'am. It's capacitor reactance. It's R. Yeah,
R,
it's
it
R.
says a resistor of 12 ohm.
Yes, ma'am.
Okay.
It's
What
R.
is 14?
XC.
XC. And what is 0.1?
0.1 is XL.
Is it?
No, I don't think so. It's not reactance. It's inductance. Uh, it's L.
It's L. See, inductive reactance is a resistance of that inductive circuit.
Mm.
So you will have a resistance. Me in the sense, see, capacitive reactance. So the SI unit is ohm. Resistors resistance. So SI unit is ohm. Here this is not ohm. So identify through this only. Henry was the unit of self-inductance and mutual inductance. That is only what we've studied. And here we know only self-inductance
Yes,
is
ma'am.
used. Okay. So here instead of the values of XC, XL and XCXL, resistance is given as 12 ohm. XC is not given, so we'll just have the value of the capacitance. C is given as 14 ohm and L is given as 0.1 Henry. Okay, here we have capacitive reactance. XC is mentioned as XC. Okay, R is given, XC is given. So two things we already have from what we require. See, this 200 volt, this is the ERMS. Whenever it says no, AC supplies this voltage, this frequency.
Mm.
So that is your
Okay, ma'am.
ERMS. Okay. So from here, this is the ERMS, that is 200 volt, and frequency, linear frequency. This symbol is called nu, nu. So this symbol
Yes,
nu
ma'am.
is given as 50 hertz. Now, tell me, to get the current, what should be the formula? When it says current in the circuit, if ERMS is given, it means it is answer
ERMS
is equal to
is equal to ERMS by Z.
by Z. Very good. So it means ERMS is present. 200 volt is given. To calculate current, we need to get the value of Z.
Yes, ma'am.
So Z is equal to XC minus XL, whatever. Right now I'm writing XC minus XL whole square plus R square under root. Yes. So it
Yes,
means
ma'am.
to calculate the Z, I need XC, XL, and R. R is there, XC is there. So what is missing?
XL.
XL. So how to calculate the value of XL?
1 by
No,
omega, not
that
1
is
by
C.
omega L,
Omega into L.
omega L,
Omega is not given, so we'll
and then
use
for omega it's 2 pi nu L.
2 pi nu. Yes. So XL will be 2. It has already said take pi as 3. So we'll take it as 3. Frequency is 50 and this is 0.1. So you will have
Yes, ma'am.
30.
Okay, ma'am.
Will it be or not?
I think so. 2, 3, 6. It's 3. Yeah, it's 30.
30? Okay. So XC and XL, now we have XL. So see, this is the case XL minus XC. This is not XC minus XL. Because see, XL is greater than XC. So this will be XL minus XC because XL is greater than XC. So see, value of Z will come out to be 30 minus 14 whole square plus what's the resistance given? 12.
12.
12 whole square under root. So this value will be first, let us find this. This is 16.
Yes, ma'am.
This is 12 square. So 12 and 16, do they make a Pythagorean triplet? This is 280, 144, and this is 286. Right. 256 and yeah, 400. So 20. 20 is the pi. They form a Pythagorean triplet. This will be 20. So this is under root 400, which will be equal to 20 ohm. So this is the value of Z that we've calculated. Now current calculating the value of IRMS, this is 200, Z we have calculated as 10. So what is the IRMS value? 10 ampere. Okay. Coming to the second part, can you tell me how can we calculate the phase angle?
There was a formula for it.
There were many formula. When we did impedance triangle, if you remember, see, you can use tan phi also, you can use cos phi also. Okay? Because both of them are giving you phi. It has not specified that you have to find cosine of phase angle or tangential of phase angle. Okay. So you calculate it anyways. You write it as inverse. Let me use cos phi is equal to r by z only. But you can, again, I'm saying you can use any of the values. So second one says cos phi is equal to r by z. So cos phi resistance is 12 and this is 20. So we can directly say phi is equal to cos inverse. This will be 3 by 5.
Yes, ma'am.
Cos inverse 3 by 5. So this is the phase angle. Got this resonance topic clear?
Yes, ma'am.
And series LCR?
Yes, ma'am.
Okay, please write down this question. Then I'll start with quality factor, Q factor.
Can you scroll down? Can you scroll down? Can you scroll down? ma'am.
Okay. See, let's start with the Q factor, quality factor. Understand what is the meaning of it, and you'll be able to write the rest of the details. See, this basically stands for Q factor. You will often see this stands for quality factor. Now, quality you are already aware of what is meant by quality. So, quality of what? Quality of your resonance. How sharp can the resonance be? How high the resonance can be? Okay, so quality factor basically tells you how sharp is the resonance. It tells about the sharpness of resonance. Okay, it tells about the sharpness of resonance. So, if I plot the graph between current versus angular frequency, the graph that we'll obtain will be like this. Or in fact, I'll tell you for different values. Let's say for this much time now here, this will give me a very high value of resonance. High resistance will be given. Because see, current is less here initially. The current
Yes,
is less, I is less. So the resonance will be more. Okay. If I take a value here, this will be moderate resistance. Moderate resistance. And if I take a very high value over here, where the current is maximum here. So this will be high value of resistance. So if you want to increase the quality factor, low resistance. So if you want to find about the quality factor of your resonance circuit, you want to know how sharp is it, what's the quality of your entire resonance circuit, what you do, decrease the resistance, because when you decrease the resistance, your current will increase and the sharpness of the resonance will increase. Got it?
yes, ma'am.
Now, see, calculatively, this definition I'll explain you once you look at this figure. Now, what we will do, let's say, this is the resonance frequency. I have marked here the resonance frequency. Okay. So the graph that you get is a bell-shaped graph, the highest resonance. This is the kind of graph that you will obtain, an inverted bell-shaped
Yes,
graph
ma'am.
that we call. Now see, here I'll mark two more points on either side of it. A value just before this and a value just after this, omega 1 and omega 2. Okay?
Yes,
Here
ma'am.
the maximum value of the current, that is the maximum value of the current, let's say this is some E naught. This I naught, this becomes I naught by root 2. Similarly, when we talk about the maximum value of EMF, this becomes E naught by root 2 in this case, when the resonance is achieved. Okay. So basically,
Okay,
the
ma'am.
quality factor is what? Q factor, Q is equal to the resonant frequency divided by this omega 1 minus omega 2. That's it. Okay. In easy terms, you remember this. Whatever is its resonance frequency, you already know. We've talked about the resonance frequency. What was its formula? Check in the notes.
Uh, resonance frequency.
You have derived it.
1 by 2 pi.
That is linear.
1 by 2.
Omega 1 by under root LC.
Oh, only, yeah, ma'am.
Omega we are talking, no, we are not talking about that.
Yeah.
Your omega R will be 1 by under root LC. Now see, the resonant frequency divided by, you just take either values of the graph. Means one value will be the resonant. One main value will be the resonant frequencies value. You take either of the values which is just lying, one is preceding it, one is succeeding it. That's it. So they are different. And this difference is known as bandwidth. So bandwidth, you must have heard a lot for devices. The bandwidth is very low, or for these devices also. Like your network is not good today, so you didn't switch on the camera because it would have consumed more bandwidth. These terms we often use for machines. So this is what the bandwidth is basically, because we are ultimately talking about the alternating current, which is used in the machines for different applications and purposes. So we can say quality factor is equal to the resonant 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 frequency by the bandwidth. Now let's come to its definition. Back to its definition. What is it written? Is it written here? It says Q factor or the quality factor of a series resonant circuit. Series resonant circuit means the LCR circuit is there, but the LCR circuit is showing the resonance condition. That is the case. Means if it is not showing resonance, we will not talk about the quality factor. This is not just normally for the LCR circuit. Okay. So Q factor, quality factor of a series resonant circuit means series LCR circuit at resonant is defined as the ratio of, means you are dividing two quantities now. Ratio of what? Resonant frequency. You have taken resonant frequency. To the difference means you're subtracting two things now. Now, what are you subtracting? To the difference of two frequencies taken on both sides of the resonant frequency. That is your omega 1 and omega 2. So you subtract these two, omega 1 minus omega 2, and you take their ratio, omega r by omega 1 minus omega 2. Now, how to choose these omega 1, omega 2 such that each frequency, the current amplitude becomes 1 by root 2 times the value at the resonant frequency. As I told you, its maximum is 1 by root 2 it becomes. Okay, whatever is the current, this is the current at the resonance, EMF at the resonance. So it will become 1 by root 2 times. Okay, 1 by root 2 times its value. So this is the definition. So Q factor of a series resonance circuit is defined as the ratio of the resonant frequency to the difference of the frequencies taken on either side or both sides of the resonant frequency. Okay, such that the current is 1 by root 2 times its current at the resonance. Now, have you got this Q factor?
Yes, ma'am.
Write it, then we'll derive. One derivation is there. Now, the importance of that derivation and all, I'll tell you later. First, you copy. Till here, have you understood?
Yes, ma'am.
Please write.
Ma'am, can you scroll down? Ma'am, can you scroll down? I'm done.
Okay. See, Basmi, there's a small derivation for Q factor. So this can come in the exam, but recently in the last few papers, this question hasn't come. But it's a part of your syllabus, so let us see. See, at resonance, Z is equal to R. Okay, that's what we studied. And here, if I say the current is becoming whatever is the current at resonance by root 2 times, means root 2 times whatever is the impedance, right?
Mm.
It is
Yes,
becoming
ma'am.
root 2 times. So can I write this as current as whatever was our main current I naught by Z for resonance, but with this root 2?
Yes, ma'am.
So root 2 Z is equal to R. Basically your entire resonance. Root 2 Z is equal to root 2 R. Why? Because Z is equal to R. Got it?
Mm. Yes, ma'am.
So this is the same equation that we write of impedance. R square plus XL minus XC whole square. This is it. This is how we write the equation.
Yes, ma'am.
I've just written what? Instead of XC, I have written 1 by omega C. Instead of XL, I have written 1 by omega L. Okay, so R square plus
Mm.
omega L minus 1 by omega C whole square is equal to root 2 times R. Now, it's a little lengthy derivation. So when you're writing this, just be careful with the steps, how you have to follow the steps. First step is you write the equation
Okay,
of
ma'am.
impedance, the way you have studied the equation of impedance. Okay,
Mm.
so if you studied the equation of impedance as under root R square plus this minus that whole square, you write it like this. But equating it with Z, and Z is equal to root 2 times now. So we are going to write it as root 2R. This is root 2 times Z, but Z is equal to R. So you write root 2 times R. Got it? Did you get it?
Yes, ma'am.
Okay. Now I'll square it. So R square plus omega L minus 1 by omega C whole square is equal to, this will be 2R square if I square this.
Yes,
Now,
ma'am.
from here, if I say omega L minus 1 by omega C whole square, this is equal to what? Tell me.
R square.
R square, exactly. So when I take the root on both the side, I'll get two values. Whenever you have the root, let's say R is equal to some under root X. When you open it, don't you get two values, plus R, minus R? Whenever
Yes,
we have
ma'am.
any square root, plus minus values we get.
Mm.
So one will be omega L minus 1 by omega C. Other one will be omega L minus 1 by omega C minus R. Means when you're opening it, this is plus R, this is minus R, the two values of the roots when you're opening it. Got it?
Yes, ma'am.
So what do we do? These two values are actually what? These are actually the two values of the resonant frequency which we chose. The omega 1 and omega 2. So one I have marked as omega 2, one I have marked it as omega L. Got it? So these are your
Okay,
main
ma'am.
two
Yes,
equations.
ma'am.
First equation and this is the second equation. So there are three major steps in this derivation. First is reaching these two equations. How to write these equations? You take the resonance condition, you put the value of impedance in terms of omega L and omega C. You take the square and finally bring out the two square roots. These will be the two equations that you get. Now using these two equations, first we will add them. Add 1 and 2. When you add them, it will be omega 2L minus 1 by omega 2L plus this will be omega 1L minus 1 by omega 1C. Sorry, here I have written L. Is equal to this R plus this minus R. Will we get this when we equate both the sides?
Yes, ma'am.
So I'm just writing things together. Omega 2L minus here plus omega 1L, and from here minus 1 by omega 2T, from this side minus 1 by omega 1T. Can you tell me what it is equal to?
0.
0. because they'll get cancelled. Now let's take
Yes, ma'am.
L common from this side. So here omega 2 minus omega 1 will be left. Minus, if I take C common, here 1 by omega 2 plus 1 by omega 1 will be left. Or let's not
Plus,
take
right? Omega 2 plus omega 1 L, right?
omega
2 plus omega 1, right? In the start.
omega 2 plus omega 2. Okay. And when I take minus 1 by C common, I'll get this term is equal to 0. Now let's take the LCM of this. Omega 2 plus omega 1 into L minus 1 by C. This will be omega 1 plus omega 2 divided by omega 1 into omega 2 is equal to 0.
Yes, ma'am.
Now, can I shift this negative sign to the opposite side?
Yeah.
So omega 2 plus omega 1 into L will be equal to 1 by C into omega 1 plus omega 2 by omega 1 into omega 2. Now can you see any two things getting cancelled?
Yeah. Omega
What?
1 plus omega 2.
Yes. Omega 2 plus omega 1 and omega 1 plus omega 2, they are the same thing. So from here,
Yes, ma'am.
value of omega 1 into omega 2 we get as L by C. L into C. L multiplied to C. See, from here I have shifted this on this side. This will be wait. Omega from here, omega 1 into omega 2. See, this I am bringing here, L I am bringing it out. So both will be divided, okay? 1 by LC.
Okay.
Is it?
Yes, ma'am.
Okay. Now, see, this was all about the omega term. No? Now, this is one of the equations that we get. So this was the second part of the derivation that I was mentioning. That you add both of these equations and you get the value of omega 1 into omega 2. All right. Now
Yes,
we'll
ma'am.
subtract the same two equations. So what we'll do, omega 2 minus omega 1 L will come this time. Earlier it was coming plus. Here also it will come minus. This will become plus. Signs will change. You're subtracting.
Yes, ma'am.
And see, this time 2R will be there. Why? R minus minus R. That makes it 2R. So instead of
Yes,
0, we
ma'am.
have 2R this time. So what do we get? We get here omega 2 minus omega 1. If I take common from both of them. From here L will be left. From here 1 by C, omega 1, omega 2 will be there. So 1 by C omega 1 into omega 2 is equal to L
Yes, ma'am.
from this equation that we got. So we can say omega 2 minus omega 1 is L plus L is equal to 2R. Is it? So we can
Yes,
say
ma'am.
omega 2 minus omega 1 into 2L is equal to 2R. So what is the value of omega 2 minus omega 1? If I keep it like this, can I say 2R divided by 2L? Can we say?
Yes, ma'am. Yes, ma'am.
So these two will be cancelled. Now see, coming to the formula of the quality factor. So what do we get here? Finally, we get omega 2 minus omega 1 is equal to R by L. Now see,
Yes,
what
ma'am.
was omega 2 minus omega 1 if you remember? From the equation of quality factor, wasn't it the bandwidth?
Yes, ma'am. It was
So
the bandwidth.
for the yes, so for the quality factor, we have the equation as omega R by omega 2 minus omega L. So omega R divided by R by L. So won't we get this?
Yes, ma'am.
Okay. Now when you put in the values of the resonant frequency, omega R is equal to 1 by under root LC. Here, Q is equal to 1 by under root LC into 1 by R. So to rationalize it, if I multiply and divide it by root L, here I am getting 1 by root LC and here 1 L is already there. Wait, let me show you this a little properly. omega r is equal to 1 by root L. See, Q is
Yes,
equal
ma'am.
to omega r, that is 1 by root LC into 1 by r into L. Same thing I've written.
Yes, ma'am.
So what I do, to rationalize it, I divide it and multiply it with root L. Now look,
Mm.
here if I take this above part, this is L, this is into root L divided by root C into R. Now look, what is root L into root L?
L.
L. So L root L divided by root C into R into L. LL will be cancelled. So quality
Yes,
factor is
ma'am.
equal to 1 by R under root L by C. This is the whole big derivation of the quality factor. Got it?
Yes, ma'am.
So recently this quality factors derivation has not come in the exam. Let's see. Please write it.
Mm. Yes, ma'am. Ma'am, can you scroll down? Ma'am, can you scroll down? I'm done.